Alright, today we're going to begin talking about continuity and one-sided limits. The continuity test for f of x says that if you want something to be continuous at c, the limit as x approaches c of f of x must exist, number 1. 2, f of c has to exist, so there's a colored in dot. And 3, those two things have to be the same. So here's the easiest way to describe a continuous function. It's easiest to see if something's continuous by looking at a graph. A continuous function can be drawn with one continuous motion. The pen is never lifted. That's the easiest way to describe a continuous function. A limit exists if the limit from the left and the limit of the right approach the same number. If the limit from the left and the limit from the right do not approach that same number, we've talked about how the limit does not exist. So the definition of continuity on closed interval is basically the same thing where it's continuous from in the open interval. Okay, that's what these parentheses mean. So from A to B, there's no holes, there's no asymptotes, there's no nothing. But it's also important to check the endpoints. So that the limit from the right of A, which is the endpoint, is equal to the function value at A, and the limit as you approach B from the left, okay, which is the other endpoint, is equal to that function value. So what we're going to do is we're going to answer these questions to begin with, and this is number 6. If you look, it says find the limit as x approaches -1 from the right. So from the right would be this direction, and the expected height there happens to be 0. I'm going to continue to say expected height for a lot of my limits questions. So the limit as you approach -1 from the left, okay, which is this way, the expected height is 1. And so since these two expected heights are different, the limit does not exist. And we've solved that on previous problems in this chapter. The next thing we can do is that we can look at a graphing calculator to figure out these answers, but we can also just do the work analytically, and that's how I'm going to do it on these screens. Feel free to type it in your calculator to see a visual of what's going on, but you can also do it analytically. This bottom part, I know, factors, and it factors into x minus 2 and x plus 2. And that's almost what the top says, but what I will do to make the top be right is I'll take out a negative. And so when I cancel, I'm left with -1 on the top, and on the bottom, when I plug in my 2, I get a 4. So -1/4 is my answer. On the next part, I'm going to multiply by the conjugate. I've seen many of these. And notice these are one-sided limits, but you can find one-sided limits by doing the same techniques as we've done on the other limits. So the limit as x approaches 9 from the left would be, we're going to distribute this out, multiply through x minus 9 over x minus 9 times square root of x plus 3. Those cancel, and I'm left with 1 on the top. On the bottom, when I plug in the square root of 9, I have the square root of 9 plus 3, which would be a 6 on the bottom, so my answer is 1/6. Moving forward on these problems, again, this one says look at it on a graphing calculator and then do the work analytically. This is a piecewise function. Each calculator is different in typing in their piecewise functions. You are capable of doing that on the graphing calculator, but there is different techniques in doing that on each calculator. What we're going to do is just analyze this do this analytically. Polynomials, and these are called polynomials, are always continuous. So there's one point where we have to see whether or not it is continuous. So whether or not this limit does exist. So we're going to check the limit as x approaches 2 from the right, and we're going to check the limit as x approaches 2 from the left, and we're going to see if we get the same number. So from the right would be numbers like 3 and 4. That would be this function right here, negative x squared plus 4x minus 2. And from the left would be functions like the top one. So when we plug in 2 here, we end up getting negative 4 plus 8 minus 2, which gives me an answer of 2. And down here, when I plug in 2, I get 4 minus 8 plus 6. And I end up with negative 4 plus 6, which is a 2 also. So the limit, because they both go the same expected height, is 2. Alright, in this problem I'm asked to discuss the continuity of the function. If you remember, we described continuity as being able to trace a line without lifting up our pen. Now, if you look at that, when I traced it, I had to lift up my pen because I had to jump over the circle. Therefore, it's not continuous everywhere. So the easiest way to discuss the continuity is by saying that it is continuous everywhere. So I'll write that. Continuous everywhere except when x equals negative 1. The next problem asks me to also discuss the continuity as a function. This time they don't give me a picture. So what I have to do is I'm looking on the closed interval from negative 3 to 3. The closed interval means that negative 3 is less than or equal to 2, less than or equal to 3. If you did not realize what a closed interval was, it uses brackets if it's greater than or less than or equal to, or greater than or equal to signs that use brackets. So what I'm going to do is think about what's taking place. I have square roots, and square roots, I know that you can't take the square root of a negative number. So as long as these numbers don't give me a negative number underneath the square root, I will be okay. So what I'm going to do is I'm just going to do some tests. I'm going to try negative 3 in there to see if I get a negative number underneath the square root. And I don't. I get 9 minus, this happens to be 9, so I get the square root of 0. That's okay. If I plug in negative 2, I get 9 minus negative 2 squared. That's still a positive number underneath the square root, so it is continuous. And then if you check some of these positive ones, you would also get the same numbers. So this one happens to be continuous everywhere. There are no bad numbers on this particular interval. Number 34 here, I'm going to discuss continuity from negative 1 to 2. Now if you look at negative 1, that's going to work out just fine and give you a nice whole number. What you really want to look at is if you factor this, what will give you 0 on the bottom of the fraction? Well, the number that gives you 0 on the bottom of the fraction happens to be 2 and negative 2. So those are the only two bad values, would be 2 and negative 2. So because 2 is part of my interval, though, I'm going to have to say that it's continuous everywhere, except at x equals 2. And this last part here, find the x values at which f of x is not continuous. So now we're talking about where is it not continuous. Which of these discontinuities are removable? Removable means that they're a whole. Non-removable would mean that they're an asymptote. So if I look at factoring the bottom here, I'd have x plus 2, x minus 1. So looking at how this simplifies, this would be an asymptote, okay, and it's non-removable because you can't cancel it, and it makes an asymptote. Whereas this one would be hidden on a graph. This would be a hole on the graph, and it would be considered removable because you could fill in that hole quickly. The asymptote you can't fix. It's not an easy fix, so it's considered non-removable, where a hole is considered removable because you could fill it in. And the last one here, I know that this is a straight line, so I know it's continuous everywhere. And I know this is a parabola, and I know it's continuous everywhere. The big question mark is what's going on here and here. So I'm going to check the limit as x approaches 1 from the right, and I'm going to check the limit as x approaches 1 from the left. Really all that means is I'm plugging in these two numbers to see if they meet up. So if I plug in from the right, that would be for the x squared, which the limit of that would be 1. And then if I plug in from the left, that would be this line. And when I plug in 1, I would get 1. So this happens to be continuous everywhere. There are no discontinuities.